Have you ever looked at a towering skyscraper or a massive bridge and wondered, how on earth did they build that? It's a brilliant question, and honestly, the answer is all around us. It's called construction engineering. This isn't just about mixing cement or laying bricks. It's really the science and art of turning an idea on a piece of paper into a solid, safe, and useful structure that we can all live in, work in, or drive across. It's the grand plan that ensures our buildings don't fall down, our bridges don't wobble, and our homes keep us warm and dry. Construction engineering is, the invisible force that shapes the world we see every single day, from the smallest house on your street to the biggest stadium in the country. Think of it like a massive, incredibly complex recipe. Before a chef even thinks about turning on the oven, they need a detailed list of ingredients and a step-by-step guide. Construction engineers are the master chefs of the building world. They figure out exactly what materials are needed, how strong they must be, and the precise order in which everything must be put together. They work with architects, who design how a building looks, to make sure that beautiful design is also strong and practical. They are the problem solvers who make sure a vision becomes a reality, safely and efficiently, ensuring that every single part works in perfect harmony with the rest. Without these clever engineers, our cities would look very different. We wouldn't have the incredible structures that define our skylines or the essential infrastructure that makes our lives easier. Every road, tunnel, dam, and airport is a testament to their skill. They are responsible for making sure these huge projects are completed on time and within budget, which is a massive challenge in itself. They have to think about everything, from the type of soil the building will sit on to the weather conditions it will have to endure for the next 100 years. It's a job with immense responsibility, because the safety of thousands, even millions of people, rests on their calculations and decisions. So, why is this so important? Well, imagine a world without it. We'd be living in structures that might not withstand a strong gust of wind or a heavy downpour. Our cities couldn't grow upwards, and we wouldn't have the complex networks that supply us with water and power. Construction engineering is the backbone of modern civilization. It provides the safe and reliable framework for our society to function and flourish. It's the essential link between a brilliant idea and a physical, lasting legacy. It allows us to build bigger, safer, and more ambitious projects than ever before, constantly pushing the boundaries of what is possible. Before a single shovel hits the dirt, a building has already been built many times over, but not with steel and concrete. It's built with data, lines, and pixels. This is the planning and design stage, the crucial first step where every single detail is meticulously thought out. Traditionally, this was all done with enormous sheets of paper covered in complex lines and numbers, known as blueprints or engineering drawings. These drawings are like the building's DNA, containing all the information needed to construct it. They show the exact dimensions of every room, the position of every door, and the thickness of every wall. It's a universal language that all construction professionals understand. These drawings are incredibly detailed. There isn't just one master plan. There are many different sets. One set will show the architectural design, the look and feel of the building. Another set, created by structural engineers, will detail the skeleton of the building, the columns and beams that hold it up. Then there are drawings for the electrical systems, the plumbing, and the heating and ventilation. Each drawing is a layer of information, and when you put them all together, you get a complete picture of the final product. It's a painstaking process that requires immense precision, as a tiny mistake on paper could become a huge, expensive problem on the construction site. But today we have something even better than paper. We have the magic of three-dimensional technology. Instead of trying to imagine a three-dimensional building from flat, two-dimensional drawings, engineers can now create a fully interactive three-dimensional model on a computer. This is a game changer. It's like having a digital, transparent version of the building right in front of you. You can spin it around, look at it from any angle, and even zoom in to see how the tiniest components fit together. This technology is often called Building Information Modeling, or BIM, and it has revolutionized the planning process. Using these three-dimensional models, engineers and architects can take a virtual walk through the building long before construction starts. They can check for any potential clashes, like a water pipe running through the same spot as an electrical conduit, a common problem that used to cause major delays. With a three-dimensional model, these issues can be spotted and fixed with just a few clicks of a mouse. It allows everyone involved in the project, from the client to the construction manager, to see exactly what the finished building will look like and how it will function. This incredible foresight saves time, reduces waste, and helps create better, more efficient buildings. Every great structure, no matter how tall or magnificent, relies on something you almost never see: its foundation. The foundation is the critical link between the building and the earth. Its job is to take the entire weight of the building, every floor, every wall, every piece of furniture, and every person inside, and transfer that massive load safely into the ground. If the foundation is weak, the entire building is at risk. That's why engineers spend so much time studying the ground on which they are about to build. They take soil samples and conduct tests to understand its strength and stability, ensuring the ground can support the immense pressure. There are different types of foundations, and the one an engineer chooses depends on the size of the building and the type of soil. For a typical house, you might have a shallow foundation, like a concrete slab or strip footings. These spread the weight of the house over a wide area, just like snowshoes help you walk on snow without sinking. But for a towering skyscraper, you need something much, much bigger. These giants require deep foundations, which act like long legs that reach deep into the ground until they hit solid rock or a very stable layer of soil. These are often made of massive concrete pillars called piles. The process of building a foundation is honestly a marvel of engineering. First, a large hole is excavated. Then, a strong cage of steel bars, known as rebar, is carefully assembled. This steel skeleton provides tensile strength, which is the ability to resist being pulled apart. Concrete, on the other hand, is incredibly strong under compression, or being squeezed. When you combine steel and concrete, you get reinforced concrete, a super material that is perfect for foundations. Once the steel cage is in place, wet concrete is poured in and around it, filling every gap. The concrete then has to cure, a chemical process where it hardens and gains its immense strength. This stage is absolutely crucial, and there is no room for error. A poorly constructed foundation can lead to all sorts of problems later on, from cracked walls to an uneven building. It's the anchor of the entire project. Think of the famous Leaning Tower of Pisa. Its iconic tilt is the result of a foundation that was too shallow for the soft ground beneath it. Modern construction engineers learn from these historical examples, using advanced calculations and soil analysis to design foundations that will stand firm for centuries. It's the unseen hero of every building, providing the solid, unwavering base upon which everything else is built. Once the foundation is solid and ready, the building begins its journey upwards. This is where we see the skeleton of the building, its structural frame, take shape. This frame is the primary support system, responsible for holding the building up against gravity and resisting other forces like wind or even earthquakes. Just like our own skeletons support our bodies, the structural frame supports every floor, wall, and the roof. For most large buildings, this frame is made from two key materials, steel or reinforced concrete. The choice between them depends on the building's design, height, and the specific needs of the project. The building blocks of this skeleton are columns and beams. Columns are the vertical pillars that stand tall, transferring the weight from the floors all the way down to the foundation. You can see them in large open spaces like parking garages or office building lobbies. Beams are the horizontal members that span between the columns. Their job is to support the weight of the floors and transfer that load sideways to the columns. Together, columns and beams form a grid-like structure, a strong and rigid framework that creates the shape of the building and the open spaces within it. It's a simple but incredibly effective system. The assembly process is kind of like putting together a giant high-tech construction set. If the frame is steel, massive steel beams and columns are manufactured in a factory to precise specifications. They are then transported to the site and lifted into place by towering cranes. Skilled ironworkers then bolt or weld these huge pieces together, working at incredible heights with amazing precision. If the frame is reinforced concrete, wooden or metal molds called formwork are built on site. Steel rebar cages are placed inside the formwork, and then concrete is pumped in. Once the concrete cures, the formwork is removed, revealing a solid column or beam. This stage of construction is often the most dramatic. It's when the building grows rapidly, and you can finally see its size and shape emerging from the ground. Engineers use highly detailed three-dimensional models to plan the exact sequence of this assembly. They can simulate the entire process on a computer, ensuring that each piece fits perfectly and that the structure remains stable at every stage of construction. This careful planning is essential for safety and efficiency, making sure that the building's strong and resilient skeleton is built correctly, piece by piece, as it reaches for the sky. With the sturdy skeleton of the building in place, it's time to give it some skin. This is where walls come in. We often think of walls as simple dividers that create rooms, but in construction engineering they play several vital roles. There are two main types of walls: load-bearing walls and non-load-bearing walls. Load-bearing walls are part of the building's structural system. Just like columns, they help to carry the weight of the floors and the roof above and transfer it down to the foundation. In many smaller buildings, like houses, the exterior walls are often load-bearing, made from materials like brick, concrete blocks, or reinforced concrete. Non-load-bearing walls, on the other hand, are primarily there to define spaces. They don't carry any weight from the structure above them. They only have to support their own weight. These are often the interior walls that separate your living room from your kitchen or your bedroom from your bathroom. In large steel frame buildings, even the exterior walls are often non-load-bearing. These are called curtain walls. They are like a skin or a curtain that hangs off the structural frame, keeping the weather out and giving the building its finished look. These can be made of glass, metal panels, or precast concrete. But a wall is much more than just a single layer of material. Modern walls are complex, multi-layered systems designed for performance. The outer layer, known as the cladding, is the building's first line of defense against rain, snow, and wind. Behind that, there is often a weather-resistant barrier to stop any moisture that gets past the cladding. Then comes a thick layer of insulation, which is crucial for keeping the building warm in the winter and cool in the summer. This helps to make the building energy efficient, saving money on heating and cooling bills. It's like putting a warm coat on the building. Finally, you have the interior finish, which is the surface you see and touch inside the room, usually drywall or plaster. Within the cavity of the wall, there's a hidden world of pipes for plumbing and wires for electricity. Engineers and architects use three-dimensional models to meticulously plan the layout of these systems within the walls, ensuring everything fits without conflict. So, the next time you look at a wall, remember it's not just a simple divider. It's a sophisticated, engineered system that provides structure, protection from the weather, thermal comfort, and a home for the essential services that make a building functional. The final major piece of the structural puzzle is the roof. The roof is the building's ultimate protector, its shield against the elements. Its primary job is to keep rain, snow, and sun out of the building, but it also plays a significant role in the building's overall stability and energy efficiency. Just like foundations and walls, roofs come in many shapes and sizes, from the simple pitched roofs you see on houses to the vast flat roofs found on commercial buildings and factories. The design of the roof depends on the climate, the style of the building, and the materials being used. The structure of the roof is built on top of the building's main frame. For pitched roofs, this structure is typically made of a series of triangular frames called trusses. The triangle is an incredibly strong shape, which makes it perfect for spanning large distances and supporting the weight of the roofing materials and even heavy snow. These trusses are often made of wood for houses or steel for larger buildings. For flat roofs, the structure is usually made of horizontal beams, similar to the ones used for the floors, designed with a very slight slope to allow water to drain away. Once the roof structure is in place, it needs to be covered. This involves several layers, each with a specific job. First, a layer of sheathing, usually plywood or a similar board, is laid over the trusses or beams. This creates a solid surface. On top of that goes a waterproof membrane called an underlayment. This is a critical secondary barrier that catches any water that might get past the final roofing material. It's like wearing a waterproof jacket under your coat on a very rainy day. This layer is essential for preventing leaks and protecting the structure below from water damage. The final layer is the visible part of the roof, the material that faces the sky. This could be anything from traditional clay tiles or slate to asphalt shingles, metal sheeting, or even a living green roof with plants. The choice of material affects the building's appearance, its durability, and its cost. Engineers must ensure that the roof structure is strong enough to support the chosen material. putting a heavy slate roof on a frame designed for lightweight shingles would be a recipe for disaster. The roof is the crown of the building, and its careful construction ensures the entire structure beneath it stays safe, dry, and protected for many years to come. Building a structure is not just about making individual parts, it's about how those parts connect and work together as a single unified system. This is the art of assembly, a complex dance of logistics and precision engineering. Every connection point, from where a beam meets a column to where a wall meets the foundation, is a critical point of stress. Engineers design these connections with extreme care, using detailed calculations to ensure they are strong enough to handle all the forces they will experience throughout the building's life. A building is only as strong as its weakest link, and these connections are often where the greatest challenges lie. Think about how different materials are joined together. Steel beams are connected to steel columns using heavy-duty bolts or by welding them together to form a seamless joint. When a concrete beam meets a concrete column, the steel reinforcement bars, rebar, from each part are overlapped and tied together before the concrete is poured. This creates a continuous steel skeleton embedded within the concrete, allowing forces to flow smoothly through the joint. Even the connection between a brick wall and a concrete foundation requires special ties and mortars to ensure they are bonded securely and can move slightly without cracking. This process of assembly is where three-dimensional modeling truly shines. Before construction, engineers can use BIM software to create a detailed digital twin of the entire building. They can zoom in on every single connection and see exactly how it is meant to be assembled. They can create step-by-step animated instructions for the construction crews, showing the precise sequence for lifting and fastening each component. This level of virtual planning helps to identify potential assembly problems before they happen on site, preventing costly delays and dangerous mistakes. It ensures that the thousands of individual pieces come together exactly as planned. From the ground up, the building is a system of interconnected parts, each relying on the others. The foundation anchors the columns. The columns support the beams hold up the floors, the walls enclose the space, and the roof protects it all. Every element is designed to transfer loads down a specific path, safely into the ground. It's a carefully orchestrated chain of command. Understanding how all these parts fit and work together is the essence of construction engineering. It's about seeing not just the individual bricks and beams, but the entire magnificent system as a whole. The principles of construction engineering are not just theories in a textbook. They are the reason we have some of the most breathtaking structures on Earth. Take the Burj Khalifa in Dubai, the tallest building in the world. To stand that tall, engineers had to design a unique Y-shaped foundation and structure to resist the powerful desert winds. They used a buttressed core, a strong central pillar supported by 3 wings. This design was perfected using advanced computer simulations and wind tunnel tests long before the first piece of steel was put in place. The building is a towering example of how engineering pushes the limits of what is possible. Another incredible example is the Millau Viaduct in France, one of the tallest bridges in the world. Its slender, elegant towers and cables look almost delicate, but they are the product of incredible engineering. Engineers had to design a structure that could withstand high winds sweeping through the valley below. The bridge deck was actually built on the ground and then slid out horizontally across the valley, section by section, a monumental feat of construction planning. Three-dimensional models were essential for this process, allowing engineers to plan every move with millimeter precision and ensure the bridge remained stable during this risky phase of construction. This is where three-dimensional technology becomes more than just a planning tool. It becomes a way for everyone to understand the project. With a three-dimensional model, clients who may not be able to read complex blueprints can take a virtual tour of their future building. They can see what the view will be like from their office window, or how sunlight will move through a room during the day. This helps them make better decisions and feel more connected to the project. For the construction team, it provides an unambiguous guide, reducing misinterpretations and errors on site. It's like having an interactive instruction manual for a billion-dollar project. These technologies allow us to visualize the unseen. Engineers can use three-dimensional models to show how the hidden network of pipes, ducts, and wires will be installed inside the walls and ceilings. They can run simulations to see how the building will perform in an earthquake or how people would evacuate in an emergency. This ability to see and test the building in the virtual world before creating it in the real world is one of the biggest advancements in the history of construction. It leads to safer, more efficient, and more sustainable buildings, turning ambitious digital dreams into solid physical reality. As we've journeyed from the initial spark of an idea to the final placement of the roof, one thing has become clear. Construction engineering is the essential craft that builds our modern world. It is a discipline that blends the creativity of design with the certainty of science. It begins with careful planning, where every detail is mapped out, first on paper and now in sophisticated three-dimensional models that allow us to walk through a building before it even exists. This digital foresight is the first step in ensuring a project's success, saving time, money, and preventing problems down the line. We then move to the physical realm, starting with the most critical and often unseen element, the foundation. This solid base, scientifically designed for the specific ground it rests on, is what gives a building its strength and stability. From there, the structural frame of columns and beams rises, a skeleton of steel or concrete that defines the building's form and carries its weight. Then come the walls and the roof, the building's skin and shield, which are not just simple surfaces but complex systems designed for protection, insulation, and performance. Each step is a logical progression, building upon the last. The true genius of construction engineering lies in how all these different parts, foundation, frame, walls, and roof, are brought together. It is a symphony of connections, where thousands of individual components are assembled to act as one cohesive structure. Every bolt, every weld, and every joint is carefully designed to manage the immense forces at play. This intricate process of assembly, guided by detailed plans and digital models, is what transforms raw materials into the safe, functional, and inspiring spaces where we live our lives. It's a testament to human ingenuity and our ability to cooperate on a massive scale. Ultimately, construction engineering is about more than just buildings. It's about creating the future. The structures built today will stand for generations, shaping our communities and defining our landscapes. The engineers behind these projects carry a profound responsibility to build safely, sustainably, and with an eye toward the needs of tomorrow. As technology continues to evolve, they will have even more powerful tools to design and build structures that are smarter, greener, and more resilient than ever before. It is a field that is constantly learning and improving, ensuring that the blueprint of our world is one of strength, safety, and endless possibility.